Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in PHYSICSSIRJEE Originals, and I have brought forward to you an interesting concept of a photon gas in a Carnot engine or a Carnot cycle. So this is a problem that has been already mentioned in a JEE Mains 2015 paper. So the idea stems from that question, and since JEE Advanced is always interested in multi-conceptual, unique, interesting questions, so this could be a potential JEE Advanced question in the upcoming examinations. Okay, so with all those exciting prospects in hand, let's move forward to see the question that was actually a part of the PHYSIKA 2021 round 2. Okay, so here's the problem statement in case you have not attempted the exam. So I would request you to pause the video here, read through this problem statement here, and also the options that are given below. One or more than one correct option may be chosen. Okay, so after a fair try, do come back for the concept explanation, the solution, and also the 5 practice problems at the end, keeping in mind the varied level of difficulties ranging from JEE mains to advanced and to Olympiads. Okay, so here we go. A container with a piston shown in the figure has a photon gas characterized by state equations of internal energy as functions of temperature and volume, and pressure as a function of temperature. So U is given by a constant times V T power 4, and pressure is given by a constant times T power 4, where B is a dimensioned constant and V is the volume of the system. T is its temperature, that is temperature of the walls, which becomes the temperature of the system. Let's take the gas through a Carnot cycle starting with volume of 0. You can start it with any volume. Here in the problem statement, he's talking about V equal to 0. And temperature of the enclosure being T high or TH. And sequentially take it through the standard 4 processes which encapsulate the Carnot engine. Okay, so first one is isothermal expansion, second one is adiabatic expansion, and then we have an isothermal compression to 0 volume, and at that 0 volume we heat it back to the initial temperature. So this is the idea that we are going to look at. So mark the following options. So first one is about the process 2, which is the adiabatic expansion. He's requesting whether the enclosure behaves as perfect reflector for photons. Okay. The second one, the change in entropy of the photon gas during process 3, which is the isothermal compression, is given by this expression. You have to check it. The process equation for the process 2, which is the adiabatic expansion, is PV power 4 by 3 is constant. We have to derive whether it is true or not. Ratio of number of photons in the enclosure at a given volume of V1 by 2, but during different processes 1 and 3 is given by 4th powers ratio of the temperatures at that place. Okay, so these are the 4 statements we are going to look at. So I hope you have given it a fair try. I'm moving forward with the concepts first. So before we do that, a very important announcement that I've already made recently in the community post, that in our website, that is a PHYSICSSIRJEE.in, all the playlists and the videos of the chapter-wise sections have been updated till the latest videos, and you can go ahead and have a very thorough revision for the upcoming JEE advanced examinations. It is very convenient. If people find the channel convenient, they can go ahead, and the people who are in the website, they will be able to go through the same thing. So this is done for the sake of the comfort for JEE aspirants. Okay, so and also please, a humble request, as I always do, a lot of effort goes into making of these videos with my offline job. So to keep my morale up and also the channel alive, I would request you to smash the like button, especially when you like the video, right? It doesn't take much time. And 750 likes or 300 subs more, I'll come up with the next important video. I'll try to put as many as possible, but this condition is going to keep me going. Okay, so thanks for all the unconditional support that you have put up. Okay, so before we move on to the solution, I already have taken up a photon gas concept nearly 10 months ago, based on a JEE Mains 2015 question, in which same state equations for internal energy and pressure were given. So this question was an extension of that, and the present PHYSIKA question is a further extension of that. So in the near future, whether it is this year or the coming years, JEE will definitely touch upon this concept. So I would request you to go through this video of photon gas undergoing a free expansion in that problem. Link of that problem is in the description below or the I button above. So please make sure you go through that and then come back here. Okay, so I'll take up the gist of what we learned in that video very quickly, which we can use in this problem. So important points about photon gas and its comparison with ideal gas, right? So we talk about ideal gas distributions and state equations. So in photon gas, in the question itself, it has been given this way, right? So if you have an enclosure where photons are going back and forth, right? So number of photons you should realize is not a fixed number. That's the one major difference between a photon gas and an ideal gas. In ideal gas, when you have a closed container, you don't have the molecules increasing or decreasing in number. Molecules are neither created nor destroyed, but photons actually are either absorbed or emitted by the enclosure walls. So they are not fixed, unlike the gas molecules in ideal gas system. Second important point we learn is that if you go through these two equations, the pressure and temperature are directly related to each other. So you don't have pressure as a third independent variable. So the volume and temperature T are sufficient two state variables that uniquely define a photon gas system state. Unlike here, in ideal gas, we require all three state variables, pressure, volume, and temperature, to uniquely define a state. So in terms of calculations and comparisons and problem solving, actually photon gas system is a much easier system. It's not famous, but it's much easier system to solve. That was the motive behind picking up this particular concept for the PHYSIKA examination. For a photon gas, the only possible type of heat process is via radiation. So in gases, normal ideal gases, we supply heat in many forms, but in photon gas situation, the only type of heat supply will happen is in the form of radiation, and that radiation comes from the walls of the container. So these walls either give or take the photons. So you can imagine the amount of heat going in is based on the fact that the walls actually spit out photons. It's like a spray. They give out or they absorb the photons. Okay, so that is, energy can be exchanged with the container only by the emission and absorption of photons. An adiabatic volume change requires that the container walls be perfectly reflecting mirrors. Okay, right. So if the process is supposed to be an adiabatic process, then since the radiation cannot happen, that means the number of photons remains same, which means whatever photons are there, they come and hit and go back. That means in that process, that is an adiabatic process, the walls should be a perfect reflectors. They can't absorb and they can't emit. And that was one of the options, by the way. We'll go back and mark. Okay, so with that, let's now start with the concepts that are required for this problem. That is a Carnot engine. Any Carnot cycle require two important processes. One is the isothermal one, and the other is adiabatic. We'll go step by step. A lot of things are on the board. So I would request you to, instead of reading things on your own and making it clumsy, just follow my lead. Look at where I'm pointing, listen to me carefully, it will be all fine. Okay, right. So here you could see I picked up the part or the state equations that were mentioned in the question. Remember, as JEE aspirants, you need not mug these ones up. If JEE has to ask a question, like in the previous mains one, they will give you these state equations. Okay, so these are based actually on your Stefan-Boltzmann law, which you can actually derive also. So, but JEE will not be interested in all those. You could see that T power 4 is a major Stefan-Boltzmann law understanding. Okay, so now let's go ahead. With isothermal process, that means a constant temperature process, you could clearly see it is also a constant pressure process, with B being a constant. So that's one major difference, right? Because of these two state variables only, the constant temperature immediately implies that it is a constant pressure process, unlike our ideal gas. Now let's try to write in an isothermal case only. All these green equations that I wrote are in isothermal case. So what is the value of du? In an isothermal process, once the temperature is constant, you'll get Bt power 4 into dV. But Bt power 4, can you see, can be written as 3 times pressure. That's what I wrote here, which is interesting. And dW, we all know, is a PdV work. Okay, right? So using first law, du plus dW gives you 4 PdV. And if I do it for a substantial condition, that is, if I change this dq to a delta q, some textbooks write delta q. I don't like delta q because q is not a state function. I use q for a delta q. Okay, so q value should be integral of 4 PdV. And since in this problem, it's a constant pressure, P comes out, you'll get P4 P delta V. and I substituted P for this, you'll get a 4/3 BT power 4 delta V is the value of Q in an isothermal process. Now we take this opportunity to define delta S for this. And remember, S is a entropy. Entropy is a state function. Okay, so even though we derive it in isothermal process, just like U, we can claim it is true for any state. Okay, so we take this opportunity to define delta S, which we all know is Q divided by T for that process. So when I divide this by T, I end up getting 4/3 BT cube into delta V. And you already know that this happened because the T value was constant. You could dare to write this S as 4/3 BT cube into V itself, right? So from delta V, I changed it to V itself, as you can clearly see. Okay, so there is no volume. And how you might say, how can you change delta V to V? Plus constant should be there, right? I'm assuming if volume is 0, there is no photon gas, there is no entropy. Okay, so that's a very standard assumption that we can make. So S is equal to this becomes the entropy form, and that gives you an idea about one of the options. So let me go back and check which processes were given, so and which options were given. So we are looking at option B, the change in entropy of the photon gas during process 3. Process 3 is isothermal compression to 0 volume at a temperature Tc. Okay, so what would have been that value? Isothermal, for that particular problem, the isothermal one should have been this 4/3 BT cube into V. Instead, they have written the 1/3 there. So 4/3 was missing. This one, yeah. So this should have been minus 4/3. Then would have been right answer. So B option was wrong. Is our conclusion. Okay, right? So we'll remember that, and as we keep moving on, and we'll mark the answers finally. So the concept 2 is about, obviously you would have guessed it right, adiabatic process, how the photon gas behaves in adiabatic process. This is even more easier process. Okay, so at adiabatic process, S should not change. It's clear, dq is 0, then delta S or ds is also 0. So the value of Vt cube should be a constant. We already derived what is S, right? So just look at this. If an adiabatic process is taken, S is constant, so Vt cube should be constant. So you could see that here. And since you can write P and T interchangeably, so T can be substituted as P power 1/4 here. Okay, right, and rearranged, you'll get PV power 4/3 is constant, which was one of the options, as you could clearly observe here. So you could see the C option was all about that PV power 4/3. So we got one more answer as we move along systematically in the solution. Okay, so once that is done, as the number of photons don't change in adiabatic process, I already reiterated that in adiabatic process, that spraying of photons or absorbing of photons won't happen. The walls will behave like perfect reflectors, and for the number of photons won't change. Using this as a trick, now understand this. In adiabatic process, we got two results. One is that the number of photons don't change, and one that entropy won't change. So if there are two constants in that process, then those two constants should be proportional to each other with alpha as a constant. So this is a very nice trick that will help us solve problems quickly. Okay, so once we realize that N is directly proportional to S, where alpha is a constant, and let's try to keep all the things together and try to draw the PV diagram to give us a picture. Okay, right? So here is the PV diagram for the Carnot cycle. Okay, right? So in the first process, we have a isothermal or adiabatic process, which is shown in this manner. It's different from ideal gas, right? In isothermal process, here is an isobaric process. Then you have an adiabatic expansion. Then you have an isothermal compression to 0 volume, and then you go back. So in the last option, he asked that at volume of V1/2, which is this one. Remember, here the value of volume was V1. There are two states that are possible, one in process 1 and in another one in process 3. So at these two places, for the same volume, he asked the ratio of number of photons. Okay, right? So after, you can pause and read all how this graph was drawn. I think I've explained it properly here. So we'll go back and solve for that last option. So you know that N is proportional to S. So this is how at the bottom I tried to calculate. So N1/N2 at any stage should be ratio of entropies. Entropy expression we got from the previous slide. And it is also dependent on volume, but in the option, he wrote that it is at the same volume. So at the same volume, the ratio of cube of temperatures is supposed to be taken. Whereas if you check the answer, it was given as a ratio of 4th power of temperatures, which is wrong. So among the 4 options, let me go back and mark the correct answers in the original question, and we'll move on to the practice problems. Yeah. So the correct answers are: enclosure should act like a perfect reflector in adiabatic process. That should be perfect. And the second one was wrong because there was a 4 missing. Third one is right. We got that for an adiabatic process. And the last one is wrong because you should have had a cube ratio. Okay, so I hope you got each one of these as a concept and understanding. So let's move forward to the practice problems. Okay, so here's the practice problem 1. Right, it's an extension of the Carnot engine problem. So just I'm very curious how much you understood and how well you can do the calculations further, which could be a future JEE advanced, maybe a paragraph style question. Okay, so I've drawn another Carnot cycle for your understanding. So this is first isotherm in photon gases. You have isotherms are flat lines. Okay, so this is another isotherm. So your process is A, B, C, D, A, and this time we're not having volume equal to 0 condition, and this is a V greater than 0. Okay, so is the efficiency of this Carnot cycle when photon gas is used as a working fluid the same as the formula that we get for the ideal gas, 1 minus T low by T high? Is this true or false? Just try to answer. If it is false, give me the actual expression in terms of TL and TH. Comment your answer below along with the timestamp. I'll respond, and I'll answer this in the PHYSICSSIRJEE quiz series. Okay, so if you require and if you're faltering with the answer. Okay, so and before we move on to second practice and second to fifth practice problems, I would request you cover all the subtopic playlists of thermal physics, which is heat and thermodynamics. I made it into 4 to 5 subtopics. All of them are in the description below. So please make sure you go through them in order of the uploads and try to play as many as possible so that you get an edge over others before your JEE advanced examination appears. Okay, so that's one thing. And second important thing is that there are 2 revision series videos I have made on kinetic theory of gases. You could see the left side thumbnail, and the gas processes and thermodynamics as a part of JEE mains series. At that time, I felt that this was one of the best videos that I have made. These were all mega revision videos, 1 hour 30 minutes each, with all the concepts covered and all the important practice problems together in that. You can go through the comments of these particular videos with answers that discussions that happened. I would have continued these videos had they got good response. I still believe, even though the response was not good, these were one of the best videos in the channel. Even though it says JEE mains revision series, old students will vouch for the fact that they are equally good for JEE advanced with all the concepts being covered. So these links of these old videos are in the description below and I button above. These are the best times to revise them before the JEE advanced examination. So with those things out of our way, let's go to the practice problem 2. Again, a very interesting problem. Maybe you can solve it using the idea of radiation pressure or otherwise. Try to check this one out from the Pathfinder. Check your understanding thermal physics chapter. Okay, so comment your answer response below along with the timestamp. Okay, so quite a few will get from Pathfinder on this topic. Problem 3, it's based on, again, I'm not saying radiation pressure, but it's similar to that. I've already asked this question in another video, so I've not got very good response for this question, but this is a 2-dimensional gas kind of situation. Just try to go through this and you'll enjoy this problem. This is at a JEE advanced level. Next one, the last one from Pathfinder, and the 5th one would be even more interesting. So this is again you could say a plate hanging in the air with the help of a radiation pressure. So a very interesting one, again from the check your understanding problem. This was discussed in one of our Discord servers also. So you can join there to have a look at the solution. So or I will definitely come up with it if you struggle in the Pathfinder solution series. So last one, a very interesting JEE advanced level question between 2 parallel plates. Okay, so if 2 parallel plates are maintained at temperatures T1 and T2, and this time those plates are not black bodies and have emissive powers as E1 and E2, and emission rates are E1 and E2. Capital E1 and E2 are the emission powers, and small even e2 are the emissivities. Actually, this should have emissivities. These are emissivities. Okay, right. So the energy that is transferring from one plate to another plate has to be proved to be this expression. Okay, so because there will be reflections and emissions, there will be continuous series that you will make out of the equations is one of the ways of solution. There's another smarter way of solving this problem, which I will definitely solve in the PHYSICSSIRJEE quiz. Okay, so this is a very interesting JEE advanced level question. So with all that, and some of you would be new to this channel, I would require to tell you that there is a Discord server of this particular channel where 2000 plus JEE aspirants, serious aspirants, very good aspirants who keep sharing their own problems, and we keep having discussions. I chip in time and again, but major discussions happen among students. So if you just join the server and keep surfing through different channels in the server, one of them being thermal physics, and there is a separate channel for EMI, etc., etc. You'll find a list of problems which are very, very important for your JEE preparation. Don't become left out of this particular community or group. It's much better than the Telegram group that we actually have. Okay, so keep checking the community tab for the QOTDs. Of late, I have not been posting them because I was busy with other works. I'll continue doing so. Some nice QOTDs are being posted in the server. Okay, so what is the Discord server? If you're a complete beginner, I've made a video tutorial on explaining what is Discord, how to use it, and how to be part of PHYSICSSIRJEE official Discord server. Link of that video is in the description below, or the i.mo. Please do check it out. Also, please check all the parallel series that are running in this channel, right? So I have written only few of them. Rest of the important ones, there are 7 to 8 important series that students love and absolutely encourage me to keep doing that, so that their preparation becomes better and better. So all of them are in the description below. Take your time if you're new. Watch 4 to 5 videos per day, maybe at 1.5x speed and all that. Try to cover as many as more than 240 plus videos at the time of this upload. More you cover, more closer you will be to your achieving of potential in the JEE advanced exam. So that's what I could tell, and you would feel the same after watching 4 or 5 videos. And please don't forget the like, sharing, and subscribing to the channel. Liking is very important, and it's a free 1 second reciprocation of your love for this particular channel. And I don't think I'm asking much out of it. Okay, so I hope you'll do that, and thanks for staying this long, and see you in the next one.